Hello everyone, and welcome to section 7.2, which is solving exponential equations and inequalities. Now, a property that we have to talk about that sounds more scary than it actually is the property of equality for exponential functions. So there's the fancy math version of the explanation of this property, but really all it is if your bases are equal, your exponents have to be equal. So like we see, if 3 to the x equals 3 to the 5, then x has to equal 5. And if x equals 5, then 3 to the x equals 3 to the 5. So really it's just saying that if your exponents are the same and your bases are the same, you're golden. So the way that we're going to solve these is we're going to rewrite our questions to be in the same base. We're going to set our exponents equal to each other, and then solve as if it was a typical Algebra 1 question. So let's take a look at this one. I have 3 to the x equals 9 to the 4. Now, don't jump off too quickly and say x equals 4, because notice these are not the same base yet. I can, however, rewrite 9 as a base of 3. So I've got 3 to the x, that's going to stay. 9 is the same thing as 3 squared. And I'm rewriting it as 3 squared to the 4th for a reason which you'll see more in the next example. But remember, an exponent to an exponent we multiply, so 3 to the x equals 3 to the 8th. And our bases are the same, so our exponents have to be the same. And in this case, we don't have to solve anything. It comes right out, x equals 8. Let's take a look at another example. So again, we don't have the same base yet. So we can't just set 5x equal to 2x minus 1. We can, however, write 4 as a power of 2. So I have 2 to the 5x equals 2 squared to the 2x minus 1. So I've got 2 to the 5x. Most common mistake with rewriting these is not distributing that power to both. So equals 2 to the 4x minus 2. Be careful of that. So my bases are the same, therefore my exponents must be the same. So 5x equals 4x minus 2. Subtract 4x on both sides. And x must equal negative 2. Now the way word problems are going to look in this section is a little bit different. It's going to be kind of using the idea that we saw in section 7.1, but we're going to be solving for our B, or our rate of decay or growth. So in this particular example, in 2000, the population of Phoenix was 1,321,045. By 2007, it was estimated to be 1,512,986. Write an exponential function that could be used to model the population of Phoenix. Write x in terms of the number of years since 2000. So I know that I'm not going to have my full year as my exponent, it's rather going to be years since 2000. So let's take a look at what we've got so far. I know that my initial amount was that 1,321,045 number. They didn't tell me a rate, so I'm going to still have to have that as a B. Or if your B's sometimes look like 6s, feel free to use any other number. Our time exponent we know is going to be 7, since 7 years past 2000 is 2007. And the amount that we have sort of in the end, or after those 7 years, is that 1,512,986. So if I want to solve for B, I want to get it all by itself, so I'll divide by that 1,321,045 with a calculator, of course. And I get approximately 1.145. Alright, so I've got something to the 7th equals 1.145. If I take the 7 through to both sides, I get that my answer is about 1.0196. So if I rewrite my equation as they wished, I've got y, or p, or whatever variable you wish, equals 1,321,045. That initial amount again. our rate that we just solved for to the x. We would be able to use this equation to solve for a theorized population in 2012 by plugging in a 12, or any other year. We would just have that x be number of years since 2000. For inequalities, very similar except for the fact that we don't have equations. So we're going to rewrite into the same base again and then just solve the inequality formed by your exponents. So I see 625. I vaguely remember that that is a power of 5. So I'm going to rewrite them in the same base. And that's 5 to the negative 4th. It's 5 to the 4th, but since our answer is in the denominator, we have a negative exponent. My bases are now the same. I can set my exponents not really equal to each other, but pretty much just drop them down. I'll subtract 3 on both sides. Divide by negative 2. Recall when you divide by a negative number that you have to flip your inequality symbol. And we get x is less than 7/2. And that's our answer. Last but not least, we have to talk about money. So if we just have a what's called simple interest, you accumulate interest on money you put into the bank once a year. We use the idea that we have that 1 plus your rate to the time and then your principal amount. But oftentimes banks will compound your money, give you some interest along the way, which is nice because then you'll gain interest on interest. So we use a different formula for this to account for the times that you are getting that interest along the way. We have this new variable n, which tells us the number of times that you're compounding per year. Everything else looks the same. The only difference is that n that's both divided into our rate, which is as a decimal, of course, and then being multiplied by our time. So we're kind of accounting for it two ways, but both of those kind of balance everything out. So let's take a look. And the important thing is that you are able to identify, well, what is your n? What are these different variables? So I have my time, I see after 1 year. My amount is going to be the balance that we're going to find in the end. The amount I'm putting in is 4,000. My rate is 2.92%, which is 0.0292 as a decimal. And then our number of times compounded, quarterly and daily. So quarterly, you have to think about how many quarters are in a year, and there are 4 of them, so n equals 4. So we'll set up our equation. We have 4,000 times 1 plus that rate as a decimal over our number of times compounded, which in this case was 4, to the 4 times my year, in this case was 1. So I type that into my calculator, making sure I have all of my parentheses. So I've already got that typed in, as you can see. So you do want to make sure that your whole rate, your parentheses here is still in parentheses up there. And then that gives us, since it's money, we definitely want to make sure that we round to 2 decimal points. So $4,001.03. Not a crazy amount of interest, but you just let the money sit there, and it grew $1.03 in 1 year. Over time, say you had it in there for 20 years or 30 years, you'd be getting more and more interest based off of the fact that you'll have more money at the end of each, in this case, quarter, so you will accrue more money. That's why it's better to put money in a savings account, something that'll get you interest versus just sitting around your house. Now let's take a look at the next one. And it says daily. So daily, there are 365 days in a year, so n equals 365. Same exact setup. except my n is different. $365 times 1, because it's still 1 year. Now if I type that into my calculator, now I'm just going to hit second enter just to call up the prior entry. So I just have to edit it slightly. I get $4,001.12. So again, not a lot, but again, it was just 1 year. You didn't have to do anything for it. And the longer you keep it there, it will grow. So that's all I really wanted to talk about with 7.2. We'll look at a little bit in class, and then you'll work on your homework. So I'll see you then.